Dr. Amaya, welcome. The Zoom floor is yours.
Awesome. Thank you so much for that, John. I wasn't quite anticipating the poker, but I appreciate it nonetheless. Real quick, I want to thank the organizers and John for giving me the chance to speak with everybody. I do see John's face, so I'm going to try and minimize him, not necessarily wanting to see him the whole time. And yeah, I just appreciate everybody taking the time to come in and have this discussion today. I'm hoping that we can have some really nice Q&A at the end, and I'm hoping that you guys learned some stuff today. Because that's really the goal of what I'm trying to do, is trying to teach you a little bit about what's driving climate change and how we know that and how we perceive those changes in climate change. And so really what I want to talk about, see if I can advance my slides at all. There we go. So yeah, really what I want to talk to you about today is the perception of climate change. And when we first think about climate change as a concept, one of the first things that should come to mind is global warming. And this map right here, what I'm showing you here is the change in surface air temperature since 1860. And you can see that globally, temperatures have increased, obviously. But that's not necessarily true everywhere, and it's not exactly at the same rate. And typically what's shown in the literature and in the media is this globally average number, this 1 degree Celsius, that the world has warmed since about 1860. And really the problem with these globally average numbers is that they smooth over a lot of the complexity of climate change, a lot of the regional manifestations of climate change, and it smooths over the sort of regional and individual assessment of risk of how we perceive the impacts of climate change. And it's because we don't experience globally averaged values that this is really a problem. We don't live in the global mean. Nobody lives in the global mean, right? We live in San Diego, or I live in Seattle, where I grew up in Kansas City, right? Nobody lives in this global average. And it's really on these regional scales that we feel the impacts. When we step outside, we don't step outside and say, oh, global warming is really bad today, right? We step outside and we say, oh, I need to evacuate my house because a wildfire is bearing down on me. And that could have been, or possibly was, exacerbated by climate change, right? So this is a big problem, and this is how this has led to a communication down, sort of a breakdown of how people communicate the risks of climate change, trying to synthesize sort of these global impacts down into these regional scales, and really hammer home to individuals in localities and municipalities that climate change is an issue for them, specifically for them. And we can see that in the way that sort of the media and scientists through the media try to communicate the risks of climate change. These are 3 headlines from different newspapers that have come out this year. You can see in the LA Times, we had this headline: thanks to climate change, hurricanes pummel land longer. Or in the New York Times, Southwest droughts rival those of centuries ago, thanks to climate change. Or even in the San Diego Union Tribune, climate change helped produce San Diego's huge ocean heat wave in 2018. This was in May of 2020. These are all attempts at trying to communicate the impacts of climate change to individuals, trying to take this globally averaged value and communicate it to you and make you feel like something bad is happening to you now, because in a lot of ways it is, but we just don't have a good sense of that. And that's what I'm really going to try and hammer home for you today. But before I get going any further, I'd really like to get a better sense of who I'm talking to. Just to give you perspective of what I see, I don't see anybody, right? I just see my slides. And I sort of see the number of people that are here. But if you could, just for a second in the chat, just give me like one word about what it is you do. If you're a professor, what's your discipline? If you're a research scientist, what is your discipline of study? If you're a student, maybe just put your major and your year. If you're a freshman biology student, that'd be great to know. If you're in industry, that's great. Maybe say like, I don't know, electrical engineering, or so they're already starting to scroll through. I'm just getting some hits here. Administrator, bio student, lots of bio students. I understand that Dr. Love bribed his bio students with some extra credit to attend, so I appreciate that. Lots of bio students, awesome, cool. Environmental science, okay. Wow, lots. Wow, this is great. Yeah, and from all sorts of disciplines. So this is really cool for me because it helps me understand who I'm talking to and different ways we need to communicate what's happening here. So I'm just looking through a few more. And if you notice me looking over here, it's because I have notes over here. So I'm looking at notes, but my slides are also over here. So we're all getting used to the Zoom world, right? Cool. Okay. So I appreciate that. And so moving forward here, I want to think about how well some of these messagings that we see in the media have landed on people. And I'm particularly interested in how it's landed with people in our community I lived in San Diego the last 5 years, and I consider that part of my community. How these sort of communication devices have helped people perceive the risks of climate change. So I'm going to ask you a series of polls, and I'd love you to answer truthfully. All the answers are anonymous, so please feel free to be as truthful as you like. They're just yes or no questions. And then basically what I'm going to do is we're going to take the poll together, and then we're going to compare the results to the same poll that was taken across the nation, and see how we stack up against the national average as well as averages across the state. So with that, Adrian, you want to open up that first poll? Okay, so this first question I want you to answer is, do you think global warming is happening? I guess I have to respond too. Oh, no, I don't. And I realize as you're answering this poll, I realize that our sample is a little bit biased, especially with Dr. Love's impassioned intro, which I appreciated. But I still think it's informative. I think it's important that we ask these questions directly and honestly as possible. And whenever you're, Adrian, I don't know what you're seeing. So if you see, okay, so, and that's totally fine. So it seems like 99% of the people here believe that global warming is happening, and two answers no. That's totally fine. You're entitled to your perspective, and hopefully by the end of today we can change some opinions on that. Let's see how this stacks up against the national average here. I'm trying to change my slide. It won't let me. There we go. Okay, so this is the same question that was asked by Yale University in collaboration with different universities around the country. And 72%, the national average was 72% of adults who took this survey, something like 50,000 adults, think global warming is happening. And you can see sort of the regional distribution of what that looks like. And obviously there's a lot of things that go into the way people answer these questions, or the kinds of people that answer these questions. There's all sorts of layers to unpeel: political biases, right? Socioeconomic status, all sorts of things. But this is just interesting to see. So obviously we're more than a national average because we're sort of a selected bias group. But it's still interesting to see. So let's open up that second poll now. So do you believe global warming is mostly caused by humans? So this is a slightly subtler distinction here. You can think global warming is happening, but not necessarily believe that it's being driven by humans. And I'll just leave that to Adrian whenever she feels like it's all set. Okay. All right. So similar statistics, right? Most agree that global warming is happening, and most agree that it's caused by humans. Again, hopefully we can change some opinions after the course of this presentation. All right. So let's jump to the next poll, please. Oh, wait, I'm sorry. Before we do that next poll, sorry, Adrian, I'm going to show you the national average. 57% of the adults that took this poll agreed that global warming is mostly caused by humans. But you're starting to see sort of the degradation of this opinion. You're starting to see some of the doubts that are being stowed in the general public about man-made, human-driven climate change, because you start to see this uncertainty starting to weigh down in different regions of the world, or different regions of the country. All right, so let's do that third poll. All right, do you believe most scientists think global warming is happening? Okay. Similar statistics, right? Overwhelmingly yes, but a few no's, and that's okay. Today, I am a climate scientist, first and foremost. I'm not a political scientist. I'm not an economist. I'm not a sociologist. I'm not an anthropologist, right? I'm going to infer some things about the way people act and the way people think based on my understanding of the climate scientists. But I'm a climate scientist, and I absolutely think global warming is because of human interactions. It's due to the burning of fossil fuels. And hopefully by the end of this presentation, you'll be convinced of that as well. But let's see how we stack up against the national average once again. And this one always boggles my mind. If you just remember 2 maps ago, right? The majority of the United States, people think global warming is happening, but they don't think scientists think global warming is happening, which is a huge, again, it's a huge breakdown in communication. And it's more representative about sort of the distrust of science in this country as a whole. And you can see that national average has crept down again, down to 55%. So let's look at this last poll, please. Do you think global warming is already harming people in the US? Okay. And so this is, again, following our sort of somewhat biased theme here. But really what this question is asking is, this is a sort of a risk assessment, right? Do you perceive the effects of climate change? Do you think that it's impacting your fellow Americans? Do you think it's impacting other people in the world, right? This question is more about risk assessment. And if you look at the national average, once again, you can see that there's, hold on, let's see if I can, there we go. You can see that, again, people are uncertain, right? People in different parts of the country have a different sense, a different assessment of what the risk of climate change actually looks like, about the impacts that people are feeling now or into the future. And so this is really what I'm going to talk about today is can we think about climate change from two perspectives. One, how do scientists definitively attribute climate change to human activities? And then having done that, how do scientists quantify the perceptibility of climate change? How can they quantify if you can go outside and tell that climate change has quote unquote arrived? And then how does this impact the way that we think? How does this impact our overall political will to do environmental policy? If you think about the perceptibility of climate change, not just within the United States, but also from country to country across the globe. So we're going to start thinking about this first question first. And I'm probably primarily going to be doing this from the lens of a niche field of climate science called detection and attribution. It's this idea that we can detect a change, or we sense a change in the climate system, mostly through observations, and then we're trying to attribute it to either natural changes in the climate system, things that humans don't control, or human-driven changes, things that humans do control. And so to illustrate that for you, I'm going to use global mean surface temperature. Okay, this is I'm going to show you a lot of time series today. So let's hopefully get used to what we're looking at here. This is annual mean globally average surface temperature from observations from 1980 to 2019. And basically what you see from 1880 to 2019, you can see this general increase, right? And this is what we call global warming, with values above zero being warmer than normal and values below zero being colder than normal. And we've warmed by about 1 degree Celsius or about 2 degrees Fahrenheit. So the question is, we've detected a change, right? But really the question is, can we attribute it with any skill, with any certainty? Can we attribute it to human factors, or is it completely natural, right? The climate system has changed naturally in the past. Who's to say it's not changing naturally now? Well, one method that we use to answer this question is by using global climate models, GCMs here, global climate models. These are really large, really complicated computer simulations of the physical processes that lead to changes in weather and climate. And so basically what we do is we take the globe and we break it down into a series of grids, both in the sort of the northeast, southwest direction, so the horizontal direction, but also in the vertical. So we stratify the atmosphere into a bunch of grid cells. We put the ocean in a bunch of grid cells. We put the land surface in a bunch of grid cells. And we simulate, using our understanding of the math and of the physics, we simulate how different things evolve throughout the climate system. We simulate ocean currents, wind fields, precipitation, the interaction of rain with plants, the take-up of carbon from plants or by the ocean, all sorts of things. And really the end result is from my first slide here, right? This from my title slide here, this is a climate simulation. This is 1 year simulated by a climate model, a NASA climate model. And you can see sort of the climate system unfolding over the course of the year. And to give you a sense of how this is sped up a little bit, but you can see some of these days passing. So you see the shadow coming across, that's nighttime, that's local nighttime as it passes by. Okay, and you're just watching 1 year unfold in this model. So this is, I'm just trying to impress upon you how complicated of a situation this is, but how sophisticated these models are to be able to resolve some of these processes. And not every model is as high resolution or as beautiful as this. Some models are a little more coarse and they a little more brute force, but all these models do basically the same thing. They're basically of forward integrating the circulation changes in the atmosphere and the ocean that lead to the overall changes in the climate system. So they're really complicated, but they're really accessible. And because of that, their utility is is excellent, right? Climate models are very useful because they have a bunch of on and off switches. You can take a climate model and you can force it with a variety of different things. If you want it to look like the real world, you tell it what parts of the real world you want it to look like. So if I want it to look like the observed changes in natural, what we think of natural variability in the climate system, things like changes in solar variability or subtle changes in the Earth's orbit or volcanic eruptions that we know have happened, I can force the model with only those things. And then I can say, okay, well, how well does a model forced with those natural factors, how well does that model reproduce the real world? And if it does reproduce the real world, well, doesn't that suggest that what we've seen in the real world is just due to natural factors? So you can ask those questions. Let's say we flip that switch. Let's say we don't force it with human factors, where human factors are things like changes in greenhouse gases or ozone depletion, right? The giant ozone hole was driven by aerosols, well, not strictly speaking aerosols, but CFCs from aerosol cans, chlorofluorocarbons, or pollution, right? Pollution has shiny aerosols that reflect sunlight. It can actually cool the planet, or land use changes where we cut down forests that are dark and green and we replace them with shiny things like concrete and buildings. So let's force a model with only the natural factors, right? Let's completely remove the human influence and just simulate a planet over the last 150 years that didn't care about humans at all, that only varied based on the way we observed natural factors. And we can compare that to the observations and see how well we did. So the black here, the black line is that time series of global mean surface temperature from earlier. This is what we actually observed. And the blue and red lines here, you can ignore all the yellow for now. They're showing the simulation, the climate simulation in this model, these series of models actually, just based on natural factors. And you can see that starting at about 1960, the observations in the models with natural forcing only diverge pretty dramatically. And we cannot explain at all the last 50 years, just taking into consideration these natural factors. However, if we include other things, if we include changes in greenhouse gases, ozone depletion, pollution, land use changes, and we force our model again, in addition to the natural forcing, we get something that looks a lot better. Our models are much better at capturing what actually happened in the real world, this black line, by including things like increases in greenhouse gases. And this isn't, by the way, this isn't just a guess, right? We didn't just a priori assume that greenhouse gases are going to be the problem because we have some agenda, right? We have a very good physical understanding about why greenhouse gases lead to surface warming. And we've had that understanding for, I don't know, 150 years, right? This goes back to a very famous paper, I think in the late 1880s by, I don't know his first name, but his last name was Tyndall. And this, where he first described the greenhouse effect, this idea that CO2 traps infrared radiation that the Earth is emitting, traps it, it absorbs it and re-emits it back at the surface and insulates the planet in a way. So we have a very good understanding, physical understanding of why these changes should happen, but this is one definitive metric that climate scientists use to show that these things are true, that you absolutely need human forcing. You need changes in CO2 to reproduce the observations. So a very fair question that someone could ask, and maybe some of you are asking it right now in the chat, are CO2 changes really driven by humans, right? One sort of talking point is that CO2 changes have varied in the past, and that's absolutely true. CO2 changes have varied in the past. So how do we know that the increase in CO2 concentrations, the increase in greenhouse gases, how do we know that's due to humans? How do we know that's not completely natural? Well, one way that we can do this is by extending our record of carbon dioxide backwards using ice cores. So basically what happens is climate scientists will travel to Greenland, they'll travel to Antarctica or glaciers, really thick glaciers in high alpine regions. And they'll drill down into these really thick ice sheets and they'll get long cores. These cores can be something like a kilometer and a half long. They get samples of what we call paleoclimate proxies or paleoclimate observations of past air. So the idea here is that if you are on an ice sheet and you're experiencing snow, so snow is falling on, say, Antarctica, as the snow is falling, it traps air between the ice crystals. And as more snow falls on top of that snow from year to year, that ice or that snow begins to get compact by the added weight on top of it. Eventually that fluffy snow will be compacted into an ice crystal, a solid ice sheet. But having done that, it'll trap the air bubbles within its structure. And so if you take an ice core and you slice it into sort of like deli sliced ham sized medallions, you can see all of these trapped air bubbles within the ice core. And it turns out an ice core is about 10% air by volume. So it's a lot of air inside of this ice core. And so what this represents is a direct measurement of what the atmosphere looked like up to about 800,000 years ago. The oldest ice core that we have is about 800,000 years ago. And by doing this, we can create a nice record of what carbon dioxide looked like over the last 800,000 years. And that's what you're seeing here. That's what this red line is. It's a time series of carbon dioxide concentrations in the atmosphere over the last 800 years. But I'm purposely cutting out the present. And I'll show you where we're at here in a second. But it's totally fair to say that carbon dioxide concentrations have varied naturally over the historical period, over the geological past. And really over the geological past, it's been large changes, right? It's something like 100 parts per million increase over about a 50,000 year period. Okay, and for those of you that aren't familiar with ppm, parts per million, 100 parts per million is about 0.01%. Okay, so these changes, while they sound really small, so this is a change of about 0.01%, these are really big changes in the overall greenhouse effect that the Earth is experiencing. So relatively subtle changes in CO2 concentrations can lead to really strong surface temperature changes over the entire globe. So CO2 concentrations have varied, but look at this. Look how long it takes. It takes about 50,000 years to get about 100 ppm increase. Let's see where we are now. Right, we're way up here. Right, we're sitting very snugly above 400 parts per million CO2 concentrations these days, and we have very high resolution, very quantitative, and very robust measurements of carbon dioxide since 1958. And this is something Scripps has been doing, leading the world in measuring carbon dioxide at Scripps. But what's important to take away here is that in the present time, we've increased CO2 by about the same amount as sort of the natural carbon cycle would want to do, but over the last 60 years. So the natural carbon cycle wants to do it in about 50,000 years. We've short-circuited the carbon cycle by burning fossil fuels and increased the atmospheric concentration of CO2 by about 100 parts per million in the last 60 years. So this by itself should be sort of a red flag. And this by itself is evidence that this is driven by human climate change, particularly because the increase in CO2 is very strongly correlated with the timing of the Industrial Revolution in the late 1800s. But again, it's very fair to say, how do we know? How do we know that the increase in carbon dioxide is due to humans? How do we know that this increase isn't just spurious, that it just is some other part of the natural climate system? Well, to answer that, we need a bit of chemistry. Okay, so if we think about a CO2 molecule, it's made up of one carbon and two oxygens. And either the carbon or the oxygen atoms can be made up of isotopes. So for those of you that are unfamiliar with what an isotope is, it's basically just the same atom with a nucleus that has protons and neutrons. And an isotope is telling you how many neutrons are within that atom. And all it's telling you is basically the weight of the overall atom. So two relatively abundant forms of carbon are carbon-13 and carbon-12. And it's not important that you remember exactly what carbon-13 or carbon-12 are. You just remember that carbon-13 is heavier. It literally weighs more. An atom of carbon-13 weighs more than an atom of carbon-12. So a CO2 molecule that is made up with a carbon-13 atom is heavier. It weighs more than a molecule, a CO2 molecule made up with carbon-12, which is that lighter carbon isotope, okay? So when we think about how carbon molecules interact with sort of the biosphere, plants draw down CO2, they spit out oxygen. It's a beautiful relationship that we call photosynthesis, right? And then fauna eats the plants, right? Big animals eat plants. But what you need to understand about nature is that it's extremely lazy. Okay, plants are lazy. They prefer to take up the lighter carbon isotopes that are in CO2 molecules. They prefer to take up CO2 molecules that are made up of those lighter carbon isotopes because it's easier. They have to expend less energy to do so. So preferentially taking those up, the carbon that is fixed inside the structure of plants and inside of the animals that eat those plants is light. It's isotopically lighter than, say, ambient air, right? If you're taking out all of the light carbon atoms from the atmosphere, you're leaving all the heavy stuff back. So ambient air is heavier with respect to carbon than fauna. And this is a true relationship that's been there for thousands of years. And over the course of thousands of years, plants die, animals die. And as they die, sediment buries them, right? And as the sediment gets heavier and heavier, they start to compress and they turn into goo, and we call that goo oil. Oil is isotopically light because it's made up of the same carbon atoms that made up those plants, that made up those animals. So oil is made up of the exact same C12 that was in that CO2 molecule once upon a time in the ambient atmosphere. So how does this oil return back to the atmosphere? Well, not oil specifically, but how do the carbon atoms, those C12 isotopically light carbon atoms, how do they return to the atmosphere? Well, in the carbon cycle, on really long timescales, those 50,000 year timescales, we can think about volcanic eruptions. And obviously this is an incredible simplification of a really complicated process, but volcanoes are one source of CO2 to the atmosphere from these sort of deep reservoirs of carbon. Another source is industry, right? Industry has short-circuited the carbon cycle. You dig down, you get the oil, you burn it, and you release CO2 to the atmosphere from that oil. And because that oil is isotopically light, then we can say some things, right? I'm losing my mic. If the recent CO2 increase that we've seen, that we've observed, is due to the burning of fossil fuels, if it's because we burned oil, then the carbon, sort of the bulk average weight of a carbon dioxide molecule in air should become isotopically lighter. And that's because you're taking something that's light and you're mixing it in with something that's heavy, and you're not adding any more heavy stuff. Okay, so you just have a bunch of heavy CO2 molecules that's made up of carbon-13 that wasn't taken up by fauna, and you're adding all of this burnt isotopically light carbon molecules from the oil. And that's exactly what we see. If we look at CO2 concentrations, right, again, this is from ice cores up until about 1958, when we get instrumental records of CO2, you can see that really scary increase in carbon dioxide starting with the Industrial Revolution. And this goes starting in 1000 AD. You can compare that to the weight of air, sort of the weight of the carbon in air. You can see that it was very stable. It was very stable up until about the Industrial Revolution, where it starts to get very light. And we call this process the Seuss effect, not named after Dr. Seuss, but I think maybe Hans Seuss. He was a professor at Scripps. So I guess he was a Dr. Seuss. But he discovered this process. This provides unequivocal, definitive evidence that the increase in carbon dioxide that we've seen is from the burning of fossil fuels, because of this relationship between heavy carbon and light carbon. And it's our understanding of the relationship between greenhouse gases and the physics of how they interact with different forms of radiation that lead to global warming. So with that, I'm going to jump onto this second question here. So how do scientists quantify the perceptibility of climate change? All right, assuming that we accept that climate change is happening, whether I've convinced you that it's because of human-driven processes or not, how do we as climate scientists, how do we quantify how perceptible these changes are to an individual person, and what does that mean for how they deal with risk, or how they vote for different policies, or think they need to support financial efforts to deal with climate change? So that's really what we're going to talk about next. And it's really this battle of what we call a signal to a noise. It's this combat between the changing climate and things that want to obscure the changing climate. So a climate change signal is referred to changes in the climate system that are completely due to human activities, things that we know to be due to human activities. So things like global warming, due to the increase of greenhouse gases, right? We change the air surface temperature, as well as all the things that are impacted by warmer temperatures. So that can include things like changes in weather extremes, right? We know that hurricanes will become more intense in the future, or even currently, potentially, because of the increase in surface temperature. We also know that atmospheric circulation will be redistributed. It'll be altered by changes in the relative distribution of surface temperatures because of climate change. And this will change rainfall patterns throughout the globe. And it, in a lot of ways, is already doing that. So these are all climate change signals. Some of them are trend signals, meaning they're being shifted subtly from year to year. And it's sort of a long-term, kind of a slow slog of a trend change that is a little more difficult to perceive as a person, because our memories aren't good enough to remember what a summer's day felt like 20 years ago, or maybe you weren't alive 20 years ago, right? A human's perception of what's normal is always shifting, depending on when they grew up and how good their memory is and all that stuff. But then there's also event signals, right? Like an individual hurricane that, sure, it has some long-term trend in its statistics about how intense it is or how frequent hurricanes are. But really the impacts that you feel from climate change are on these discrete, sort of high impact and really intense events. But then there's climate noise. So what we mean by climate noise are sort of natural variations in the climate system or weather that are independent of human activities. And these are things that work to obscure signals that makes it harder to detect them, because they're noisy, right? They're really random and they're really noisy. Two examples of that are what we call climate modes. And it's not important that you know what a climate mode is. Very broadly, it's sort of a redistribution of ocean currents or atmospheric circulation that leads to a very large scale change in temperature at the surface. And this can happen completely naturally, completely independent of humans. One really good example of this is El Nino. Being from most of you, I assume, are in Southern California. El Nino is a very big deal for Southern California rainfall. So I wouldn't be surprised if you had heard about El Nino before, but that is a climate mode, and it happens completely independent of humans. It happened before us and it will happen after us. Other sources of noise are large scale weather patterns, right? I'm shocked by the number of people I meet that don't quite understand the difference between weather and climate, right? It's weather is a form of what you perceive from day to day that can completely obscure the overall signal that we're trying to understand. And it causes Congress people to walk into Congress with a snowball and say that climate change isn't happening, that global warming isn't happening. That person doesn't understand that a cold winter doesn't mean that global warming isn't happening. And to that note, what you experience, right? If you go outside and you experience a nice sunny day, or maybe you're experiencing a drought or there's a wildfire next door, hopefully not. Everything you experience in the environment every day, every month, every season, every year is some combination of these two things. It's a combination of the signal, the climate signal, and some climate noise, the change and the things obscuring that change. The climate signal is what we call deterministic. It's predictable. It's predictable in the sense that there is a cause and effect. We know that if we increase greenhouse gases into the atmosphere, we know the surface will warm. That is deterministic based on our understanding of the physics. Climate noise, by comparison, is completely random. And it's random in the sense that we don't know what the relative timing of different sources of climate noise will be, and we don't know what their signs will be. When they happen, they might be deterministic in the sense that we can estimate how they'll evolve, but the timing of the different sources of noise is completely arbitrary and completely random, and there's nothing special about the way that they unfold. But right away, you can see how this might impact an individual person's perspective of how they deal with climate change, right? In some places in the world, the climate signal is really big. Okay, and I'm going to show that to you more definitively later. The climate signal is really big, but in some places in the world, the noise is really big, and the climate signal in comparison is small. So you would imagine that the person that lives in the place where the climate noise is really big may not have as much of a sense of risk. They wouldn't be able to perceive sort of the climate impacts as strongly as someone who deals with the signal much more than the noise. So let's quantify this a little more rigorously. Let's say that we have observed some climate parameter. We're going to call it climate parameter X here. Okay, and it can be anything. It can be global mean surface temperature, it can be precipitation, it can be sea level, it can be anything. Okay, we just know that this parameter X is sometimes greater than normal and sometimes it's less than normal. And the variations, the wiggles here, are generated by noise. It's just random noise from one year to the next. And we wish that we could have observed it for 1,000 years. In reality, we've observed the climate system for about 100 years of having reliable, high resolution, sort of year to year measurements. And this is in no way enough to quantify the relative range of what the noise can produce, the range of values that X can have from one year to the next. And I'm sort of illustrating that for you here with this histogram. This is a histogram that just shows you, it's just counting the number of times a given value of X has occurred in this first 100 years. But it tells you that, sure, X varies between -2 and 2, but it doesn't tell you how frequently X is a given value relative to another. So it doesn't tell you how frequently you get a 0.5 versus a 2, because you just don't have enough samples. You don't have a statistically significant number of samples. So what happens as we observe the climate system more and more? Well, basically what I'm going to do here is I'm just increasing our observations by 100-year chunks, and I'm filling in that histogram with more and more observations. And basically, as I do this, you can see that we get a much better understanding of the distribution of values that this noise can have, that these smaller values are much more frequent than the extremes, because you can see that you have much more, you can count the number of occurrences, right? And you can see that a 1 happens much more than a 3 on this X scale. So let's zoom in on this histogram here. And we can normalize it. We can make it so instead of counting the number of times a certain value of X happens, we can say, okay, what's the probability of getting a certain value of X if you just picked a year at random? And we call that a probability distribution. Okay, so this is just showing you the probability that you get any value of X, any given value of X, just by random sample. So let's just say I picked the year 614. Okay, I got a value of say 1. Okay, I have about 18% chance of getting a value of 1 just by some random chance. Okay, and what's nice about this distribution is it has a very recognizable shape. Okay, it has this bell curve shape, what we call a normal distribution. And a normal distribution like this is not unique to climate science. This is something that happens in a lot of large sample studies. It's not the only kind of probability distribution you can get, but it's something that frequently happens. It's a way you can describe the distribution of things in climate science a lot of the time. And because this is a normal distribution, it has a very well-defined range of probabilities that we can describe the values of X as they happen. For example, 68% of the time, you're going to get a value of X that's between 1 plus or minus 1, what we call a standard deviation or a standard wiggle. So standard deviation is just sort of the average wiggle that you get over this 1,000-year time period. So on average, 68% of the time, the data is between plus and minus 1 standard wiggle. 95% of the time, the data is between 2 standard wiggles. So 95% of the time, this climate parameter X is falling between plus or minus 2 standard wiggles. 99% of the time, it's between 3 standard wiggles. And you can see that there's only a couple values that lie outside of these 3 standard wiggles. And so because this is normally distributed, we can quantify, you can quantify the noise in a really nice way. It provides you a realistic range of the values of X due to some change in noise, or sorry, due to the noise that are providing those wiggles. And so the reason why I'm telling you all this is because if we go out and we observe a change in climate change, right? If we have some signal and we want to be able to say definitively one way or the other that this signal relative to the noise is unique and that it can't be captured by the noise. It's not a part of this distribution. You can compare the signal to this distribution and get a sense for how far outside of it or how far inside of it exists. So let's say that we go outside and we measure global mean surface temperature changes and we get a change of or changes in X and we have some signal that's like 1.8. Well, we cannot definitively say that this signal is any different than any value of X that was produced by noise. So we don't know, we can't definitively say that this signal is not outside of the range of possibilities that nature could produce by itself. But if instead we measure a signal and it's way outside of the distribution, it's bigger than anything that X has produced in the past, it's bigger than anything nature could produce by itself, then you have evidence that that something else is needed to produce that signal. Maybe it's human influences, right? It's human burning of fossil fuels, for example. And so the question is, how big is big enough for your signal? Typically what we do is we say, well, the signal needs to be about twice as big as your noise to definitively say, or declare that the climate signal is significantly different from the realistic range of noise with 95% confidence. And so what that means is that 95% of the time, your noise is smaller than your signal, or alternatively, only 5% of the time can nature explain your signal. And that is sort of how we determine when the signal is bigger, much bigger than the noise. So let's do this in space. Okay, so I've described to you signals and I've described to you noise. I'm gonna use a climate model now to show you what a surface temperature signal looks like in one of these models where we can flip the switch. And I'm only forcing this model. I'm only looking at a model that's been forced with natural variability that we've observed and human changes that we've observed. So the increase in greenhouse gases, most importantly. And this is just showing you what global warming looks like in this model as a function of space. And this is the signal, right? This is how big of a change we see in surface air temperature up until about today. So this is the trend from 1950 to 2015. So it's about the kind of signal that we should have experienced up until about today. Well, we can compare this signal to a model representation of the noise. In this case, I've taken a model that's only been forced with it's called a pre-industrial control simulation. So we've taken a model that only sees pre-industrial conditions. It's just a world without humans that we've ran for 1,000 years. So we have a lot of samples of what the relative range of surface temperature looks like at each grid point on this planet. And we can measure how big the standard wiggles are. So we call this a standard deviation. This is how big one average wiggle is in any given location. You can see that in some places, there's a lot of noise. These darker blues are a lot more noise. But in some places, the signal is also really big, right? The darker reds or even the darker blues are really strong signals. But in order to get a sense of whether you would be able to perceive this signal among the noise at any given spot, you have to divide these two things. So we call this the signal to noise ratio. which just in this case is just running from 0 to 4, but anything greater than 2, so anything inside of this red line is basically saying that the signal is statistically different from the noise. Global warming is more perceptible in these regions where the signal to noise is much bigger than 2. And this is not to say that the places outside of this red line, so sort of in the high latitude Siberia or different parts of North America even, it's not to say that climate change isn't happening in those places. It's not to say that global warming isn't happening in those places. It's just to say that it's less perceptible to an individual who might live there. It's not as obvious that it's happening. And that poses a really significant challenge, right? These regional differences in the way that the signal to noise ratio is sort of unfolding really impact the way that we negotiate effective climate policy, right? I've been to a number of these conferences that are put on by the United Nations to discuss climate policy, to discuss who's responsible for climate change, who should be held accountable, how do they deal with this? Do they pay money? Do they pay reparations? How much do you need to reduce your emissions and by when, right? These are all the really important conversations that need to be had at these sorts of conferences. But the loudest voices at these conferences aren't always from the people with the most money. It's not always just the United States or China or Europe or India or like all these big world emitters of greenhouse gases. Some of the loudest voices are from places, from countries, from peoples who are in some of these more smaller countries, but in some of the most perceptible, they have some of the most perceptible impacts. So one group of people that comes to mind is this alliance of small island states. It's this group of small island countries in the West Pacific who sit smack dab in this region where the signal to noise ratio is huge. The climate signal is much more apparent than the climate noise. And they are literally losing land because of things like sea level rise. They have to lease land from the mainland so that their people can relocate. I'm thinking specifically of countries like Fiji and the Seychelles. These are some of the loudest voices at these conferences because for them, climate change is not some far-flung problem. It's happening right this second because their signal is so much bigger than the noise that they experience, and it's way more perceptible for them. So I just want to return very briefly to this initial poll that we did at the beginning of the presentation. What percentage of adults who think global warming is already harming them in the United States or harming people in the United States? Okay, and this is again, this is sort of the risk perception poll, right? How well do you perceive the risk of climate change, and how well do you know that it's impacting not just you but also your fellow Americans? And I guess I just want to make the point that it maps really strongly on this map of signal to noise, that these states sort of in the western part, west of the Rockies, have a much stronger signal to noise ratio, whereas states in sort of the southeast and sort of the high northern plains have a much weaker signal to noise ratio. Not to say climate change isn't happening for them, it's just not they don't step outside and feel it as much. They don't have as strong of it, they don't feel these as strong impacts as say Californians do. Now, of course, again, I'm not a political scientist, I'm not a sociologist. There's obviously tons of confounding things that go into this. And maybe to highlight that, we can ask a different poll. One that I didn't ask you specifically is what percentage of adults think global warming is harming them personally? And you can see nobody in the country, barely even California, above 50% thinks that global warming is harming them personally. And I see this as a huge breakdown in the communication skills of scientists and the media to communicate the impacts of climate change to people, because everybody thinks it's someone else's problem, but that is very much not true. And there's just a lot that goes into it, right? It's not just about, is it harming other people? It's about how much it's harming you. And I think this idea of signal to noise really affects the way people answer these things, and people make decisions based on this. Okay, so with that, I see we have about 10 minutes left. I also see there's a ton of questions, and I appreciate that. So with that, I'm going to transition to questions. Just very quickly, this is my email. If you'd like to talk with me personally, I'm happy to do that. Please shoot me an email. I'm always happy to talk on the phone or over Zoom or whatever. So with that, I'll just pass it back. Thanks.